Hello and welcome. Today we're going to look at circuits and potential difference. Our learning objectives are to recall that current depends on both resistance and potential difference, and the units for these are measured in amps, ohms and volts respectively. We need to represent DC circuits with conventional positive and negative terminals, use various common circuit symbols, and recall and apply the equation that links energy transferred with potential difference and charge. Here we have a series of symbols that are used to denote different components in circuits. What I'd like you to do is try and name as many as possible. So pause the video, see how many you can name, and then we'll go through and list them all. Pause the video now. The first component is a cell. Two or more cells together make a battery. Hopefully you're familiar with the bulb or lamp. Next we have a resistor. The A in the circle stands for ammeter, and the V in the circle stands for voltmeter. This is what a closed switch would look like, and an open switch. You may have encountered a light dependent resistor or LDR before. Next we have a thermistor or thermal resistor. An arrow through a component indicates it is variable, in this case a variable resistor. And finally we have a fuse. Circuit diagrams are typically shown as we see here on the left hand side as one or more loops. It is however possible to represent them, as we've got on the right hand side, as a line where the top of the diagram is the positive terminal and the bottom of the diagram is the negative. Now, in order for current to flow, there has to be a potential difference, or another way of thinking of this, if there is a potential difference, current will flow. Batteries and cells use a chemical reaction to split up the charge within the battery, sending the positive charge to one terminal and the negative charge to the other terminal. The positive terminal has a higher electrical potential than the negative terminal. Here we have the symbol for a cell and a battery. The longer line is the positive side of the battery or cell, and the shorter line is the negative side. I would pause the video now and record these two symbols in your books. Potential difference is measured in volts, using a voltmeter placed across the component or in parallel. I'd like you now to draw a circuit diagram containing a bulb, a cell and a voltmeter. Make sure that the bulb will light up and the voltmeter will read the voltage across the bulb. Pause the video now while you do this, and please make sure you use half a page for your diagram. Your diagram should look something similar to this. Potential difference is defined as the energy transferred per unit charge. Another way of thinking about this is how much energy each electron is transferring. It can also be the number of joules transferred per coulomb of charge. You do need to know this definition, so pause the video now and copy it down. What do you think is actually used up in a circuit when current flows? No need to write it down, just pause the video while you think. In the case of a battery, it's the chemicals within the battery that are used up and the energy that they contain. We're now going to move on to looking at electric fields. If you have a potential difference between two wires, you will create an electric field between them. If you place a charged particle, such as an electron, in a field, it will experience a force. Here the electron is repelled by the negative terminal and attracted to the positive terminal, which causes it to feel a force moving it upwards up the page. I'd now like you to write a sentence in your own words explaining why a battery could be said to provide a push and a pull on negative electrons in the wire. Pause the video now while you write it. An electron would be pulled towards the positive terminal and pushed away from the negative terminal. You will sometimes see lines used to represent an electric field. These field lines show the direction that a positively charged particle would be pushed if it was in that field. And this is very similar to what you may have already seen for magnets, which have field lines themselves around them. We can calculate energy transferred by timesing potential difference by charge. This is an equation that you need to be able to recall and apply. Please pause the video now and copy this down. Now for an example of how we could use this equation. An electric eel generates a potential difference of 600 volts and transfers 1.2 coulombs of charge. How much energy is transferred? First of all, we write down what we know. We know the potential difference is 600 volts and the charge is 1.2 coulombs. Then we calculate the energy transferred by timesing the potential difference, 600 volts, by the charge, 1.2, to give us an answer of 720 joules of energy transferred. If you need to rearrange the equation, you can use the equation triangle energy over potential difference times charge. Now, can you remember the definition for potential difference? If you need to, pause the video for a second and see if you can remember. Potential difference is the energy transferred per unit charge. If you look back at your equation triangle, cover up potential difference, you'll see that potential difference equals energy transferred divided by charge, or energy transferred per unit charge. I'd like you now to do the following 3 questions in your book. Pause the video while you work through it, and the answers will follow shortly. And here you have the answers. Please mark your work, and if you've missed any of the detail, please add it to your answers in a different coloured pen. Here are 3 more extension questions for those of you who'd like to try them. It's not mandatory, and if you don't want to try them, that's fine, but if you do, pause the video now. The answers will be up in a minute. And once again, here we have the answers. Please make sure you mark your work and add any detail that you've missed. Before we finish off, I'd like to offer one final challenge for those who'd like to take part, and this is entirely optional. Try to build a battery out of household objects and investigate how it works. There are plenty of resources online to tell you how to do this, and I would love to see your results. Either way, I hope you enjoyed the lesson, and thank you very much.